Okay, so let's finish up for today. So we're going to introduce one more new topic. So this has nothing to do with your assignment, but it is a new topic that I want to finish off this semester on. We'll start it today. We won't finish it today because there's something I want to finish up on the first part of class next week with it. And but it's about recursion. And so let me go ahead and share the screen with you so you can see this. Okay. And what recursion is basically is the idea of going down into the same thing over. And so it's kind of like a loop. We're gonna say it's gonna be kind of like a loop, but there's some major differences. Okay. So the idea is simply, some motivations is, what if you wanted to find all files under a directory that contain a particular word? So you would need to go down into directories, but you would also need to go down into the subdirectories and the subdirectories and the subdirectories and so forth. So you'd have to keep going down into folders inside of other folders, right? Or this H tree concept, which I won't go into too much in depth here, but another idea of how we might recursion might be useful. Okay, so basically what a recursion is that just like a method can call other methods. So you've written main methods call other methods that you wrote, call other Java methods that you didn't write, right? Your methods that you do write besides your main method can call other methods, right? What if a method were to call itself? Okay, what if a method were to call itself in order to solve its problem? Because if the problem can be defined as some work plus a smaller version of the same problem, then we can use recursion. Then we can just say, well, call the smaller problem and solve that one, right? Let me give a simple example. The factorial, okay? And so if we look at it as a factorial is, n factorial is n times n minus 1 times n minus 2. So let me do this. Let me share the whiteboard and draw it that way. This is how I would do it if I were teaching this in a classroom environment. So let me find the whiteboard. Here we go. Okay, let's see. Is there a way to? I want to move this over. Is there not a way to? Okay, well. Okay. All right, so let's say we had this n factorial, right? Okay. We understand that that's defined as n times n minus 1 times n minus 2, right? This is what the factorial is. All the way down to 3 times 2 times 1, right? Okay. With one thing is that 0 factorial is defined as 1. Okay. So what we could look at it is, n factorial, it's really just n times n minus 1 factorial, right? So we could say it's just n times n minus 1 factorial, right? So what we've said is this function, this mathematical operation, function, what we will call later, what we'll make into a method, operation, however you want to refer to it, is some work n times and then the solution to a smaller version of the problem. Right? So we could keep doing this. So n minus 1 factorial could be defined as n minus 1 times n minus 2 factorial, right? And so forth. This is a form of recursion. The function itself is defined as some work plus a smaller version of the function. All right, so let's go back to the factorial here. Okay, so factorial factorial of 4 could be explained as 4 times 3 factorial. 3 factorial could be defined as 3 times 2 factorial. 2 factorial could be defined as 2 times 1 factorial. 1 factorial could be defined as 1 times 0 factorial. But now we've gotten to a problem, right? 0 factorial, we don't want to go negative. So what we do is we define 0 factorial as 1. Hey, I don't make the rules. I don't make the rules. Okay, so my son asked me this the other day. Why is 0 factorial 1 instead of 0? Okay, or maybe he said, why is 0 to the 0 power 1 instead of 0? I don't make the rules. You're going to have to talk to your math teacher to find out why 0 factorial is 1 instead of 0. Okay? All right. Okay, all that to say. So factorial of 0, we're going to call it 1. And factorial of n, we're going to define as n times whatever factorial of n minus 1 is. Okay. So we can do that pretty simple here, right? So here we have a method called factorial. If n equals 0, that's 1. We're done, right? We have a what's called a base case definition. We'll talk about what a base case is and all that in a moment. Okay, so if it's 0, it's 1. Otherwise, if it's anything besides 0, then we return whatever n times our factorial of n minus 1 is. So if we give it a non-negative integer of 4, it ends up giving us 24, which is 4 times 3 times 2 times 1. Okay. All right. So here are some other examples. All right. Okay. Some other examples of factorials here. But if we look at how this call works, okay, so here we're saying, okay, factorial 4, when we call factorial with 4, we get 4n times, and we're going to call the method itself again, but with a lower value, 3. So then when we call factorial of 3, we're going to get 3 times whatever factorial of 2 is. 2 times whatever factorial of 1 is. 1 times whatever factorial of 0 is. But now we've hit something that returns a specific value, right? Factorial of 0 returns 1, right? So now 1 times 1 is going to give us 1, so then that's going to be 1 times 2. 1 times 2 is going to give us 2. 2 times 3 is going to give us 6. And then 4 times 6 is going to give us 24. Now you might sit here and say, wait a second, isn't this the opposite of our order of operations? Shouldn't we do things left to right? Yes, this is not showing you how the math of 4 times 3 times 2 times 1 would be done. This is showing that this method call, I'm going to get a value back for factorial of 2. Remember that this is part of the this is the method here right here. This is what's inside of when I call factorial of 3 is this thing right here. So factorial of 3 is going to return the value 6. 6 times 4 is going to give me 24. Factorial of 2 is going to return the value of 2, and then I'm going to multiply it by 3 and return that from factorial of 3. Okay, so make sure you understand this is not showing how this would be done, as a mathematical operation. This is showing that this value is what's returned from the method that then calculates this. And then that gives us this value returned from the method, and that would calculate this. And this value is returned from the method factorial of 4. Okay. Okay. So there's some parts of a recursive call that always need to be there. Let's see, is that this part of this slide or is this after this trace recursive call? Okay. The parts that must exist in recursion, since it must call itself, is 1, there must be what's called a base case. Okay. So in the case of the factorial, let's go back to show you the code on that. Okay. There's a base case, meaning that there's some value that once we reach it, we don't need to do any more work. We just need to give a value, okay, or minimal work. It may be that we call another method or something, but the base case is the end point. It's what we're trying to get to, the bottommost thing, okay? So there must be a base case. Then there must be a recursive call in order for this to be a recursive definition, meaning we must call ourselves. The method must call itself for it to be considered a recursive definition. And then finally, so there's 3 parts: base case and recursive call. Finally, the recursive call must always have what's called convergence. Okay, fancy word. Let me type it out here. Convergence. Okay, convergence, big word. It means it must go towards the base case. It must converge on the base case. Okay, so this must constantly be moving towards the base case. If it's not, if there's not convergence, we could end up in what's called an infinite recursive call, which is like an infinite loop. Or we can end up with bad results. But we must always move towards the base case. So the 3 parts, you got to remember this, okay? 3 parts of a recursive definition: base case, recursive call, convergence. Convergence towards the base case. Okay, so back to this tracing of the recursive call from the factorial and how it works with the memory and the stack and all that stuff. Okay, so here we have our main method and we have some space and memory reserved for the factorial of 4 method call. Right. Then we're going to return 4 times whatever the factorial of 3. So we're going to call factorial of 3. Okay. Then we're going to call factorial of 2, so we're going to have some space reserved for that as well. Then we're going to have factorial of 1. And then finally we're going to call factorial of 0. Now what happens here? Factorial of 0 executes and just returns the base case value. So it returns 1. So 1 gets returned into here. All right, so we return 1. Then that returns 1 times 1, which is also 1. Okay. That returns 2. 2 times 1 returns 2. 3 times 2 returns 6 into this call. And then factorial of 3, it gets 6. 4 times 6 returns 24. 24 gets returned back to the main method that called factorial of 4 to start with. Okay, so how the stack works, how the stack trace works here. Okay, all right, so that's how factorial. Okay, some other examples of some recursive definitions. What if we wanted to add up the numbers from 0 to n? Well, we have our base case is 0. Then we have n plus whatever that function at n minus 1 is. And we keep calling it until we get down to 0. This is where the convergence happens. This is how the convergence happens. This is how the recursive call happens. This is the base case. And what this would do is this would sum up, this would add the numbers from 0 to n together in a recursive way. All right. Now, recursive definitions are not the only way to do things that you may think seem to tend towards recursive ways of doing things. What I mean by that is, okay, I said that in a confusing way. Just because a problem might look like a recursive definition doesn't mean that's the best way to do it. It's not wrong, but it might not be the best way. Okay, so for example, this adding the numbers from 0 to n. We could do that using a loop, right? Or we could, there are other ways to do it as well. Factorial definitely could be done using a loop, right? What about like an example like the Fibonacci sequence? Okay, does everyone know what the Fibonacci sequence is? I'm hoping you do. Okay, so you start with 0 and 1, and each number in the sequence is the sum of the two numbers before it. So for example, 0 plus 1 gives me 1. 1 plus 1 gives me 2. 1 plus 2 gives me 3. 2 plus 3, 5. 3 plus 5, 8. 8 plus 5, 13. 8 plus 13, 21. 21 plus 13, 34. And it keeps going. Okay. We start with 0 and 1 and we move on. Okay. Now you might think this sounds recursive, right? The Fibonacci at whatever index I want to look for. So if I want to say what's the, if we start with index 0 here, what's index 8? Well, index 8 would be the sum of index 7 plus index 6, right? So it would be the sum of these two. Well, what's index 6? Well, it's the sum of index 4 plus index 5, so it'd be the sum of these two, right? So you might sit there and think this looks like a recursive thing. I mean, it's defined in terms of smaller versions of itself. Okay, and yes, that is how we define it, but one big problem in the Fibonacci, as we'll see, is that we do some work more than once. Okay, so if we look here, again, a Fibonacci solution that is recursive in nature, we have two base cases. Okay, by the way, base case doesn't mean there's only one possible base case situation. So in the Fibonacci sequence, there are two base cases. One is if we're looking at index 0. One is if we're looking at index 1. So if we have one of the first two values, then our base case is defined for those two values, and everything beyond that is defined in terms of smaller versions of itself, the recursive call. Okay? All right. So here, Fibonacci of 4, give me the sum of Fibonacci of 3 and Fibonacci of 2. Fibonacci of 2, give me the sum of Fibonacci of 1 and Fibonacci of 0. These two are base cases, so we're done. Fibonacci of 3, return Fibonacci of 2 plus Fibonacci of 1. That's a base case. Fibonacci 2, return Fibonacci of 1, Fibonacci of 0. These two are base cases, so we're done. All right, but notice something here. Notice something here. We had to calculate Fibonacci of 2 twice. That's a lot. That's extra work, right? Why couldn't we should have been able to use it here and here, right? But we couldn't because this is inside of two different method calls. So Fibonacci, while it looks recursive in nature, is actually very inefficient as a recursive solution. It's not inefficient. It's not efficient at all, especially if we pull up. Let's take a look at this. Okay, Let me show you what happens just if we go instead of Fibonacci of 4. Let's look at what happens with Fibonacci of 6. Okay. Well, we need to find out what the value at 5 is and what the value at 4 is, right? For 5, we need to find out what the value at 4 is and the value at 3. For 4, we need to find out what the value at 3 is and the value at 2. At 2 and 1. At 1 and 0. Oh, that's a lot of extra work in it. Okay. At 4, we need to find out what the value at 3 and the value at 2. At 2 and 1. At 1 and 0. At 1 and 0. Oh, I forgot to do this side over here. 1 and 0. Okay. I think that's all the oh, I didn't do 3 over here. Oh my goodness. At 2 and 1. At 1 and 0. I think all the leaves are base cases. Okay, good. But let's look at how many times I calculated Fibonacci of 2, which isn't a base case. So it's not a base case, so there is work involved in that, right? Let's see, I did it here. 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 Okay, so for here, I had to calculate Fibonacci of 2, 1, 2, 3, 4, 5 separate times. Right? That's really inefficient. Right? That is not a good solution at all. All right. So even though it looks recursive, it's not the best way to do it. Okay. Fibonacci is much better done as a what's called an iterative solution. Okay. Okay. You know, what I'm going to do here is let's talk about, let's see. Let's talk about that Fibonacci iterative solution so that we can end there today. Okay. So again, the Fibonacci, if we do it as a recursive solution here, it'll do a bunch of extra work. We've already seen how this works. Okay, I think, is there an iterative? No. Okay. So let's think about how could we do this as an iterative solution though. Okay. Well, let's create a new method. Fib. So we're going to give it the same type of header, the same type of information as the recursive version, okay? But we're going to call it iterative. Iterative simply means we're going to iterate over. It's a loop type of solution, okay? Recursive means we're calling ourselves over and over again. Iterative says we're going to iterate. We're going to make a loop instead. All right. Now, here the same thing. We still have the same situation on the base case, right? Now, an easier way to do this would be to say if index is less than 2, return index, right? Because that's kind of what's going on here, right? If index is 0, we return 0. If index is 1, we return 1. right? So if index is less than 2, we simply return the index, right? Otherwise, what? We want to start looping, right? So we want to say, we want to have long f0 equals 0, f1 equals 1, right? f2 equals 1. It'll be the sum. It'll be what holds on to the value, right? Now, what we're going to do is we're going to say for long, our iterator, our I, goes from 3, and I'll tell you why 3 in just a moment. Actually goes from 2. I is less than index. I plus plus. Okay. So what we're going to do is we're going to start looping through, and what we're going to do is we're going to keep adding the numbers to each other, okay? So we're going to say long, a temporary value is going to hold. Let's see, our temporary value is going to hold. What we want to do is we want to shift F2 into F1, F1 into F0, but we want to take our old values of F0 and F1 and make them F2, right? So we'll hold on to the F0 value. Okay. And then we're going to say, okay, now shift F0 equals F1. F1 equals F2. And F2 equals temp plus our new F0, because it needs to be the old F0 plus the new F0. Oh, I think I already put this there. Okay. All right. Now, the reason why I want to show this what's going on. Okay, so what's happening is, let me use the whiteboard kind of on the side of this here to show what's going on. Okay, so what we did here is we said, okay, I want to take this F0 container that's going to have the value 0 in it. And I have an F1 container that's going to have the value 1 in it. And I'm going to have an F2 container that has the value 1 in it. Okay. Now, each time through, what I'm going to do is I'm going to have this temp container. Okay. And the first thing I'm going to do is I'm going to take this F0 value and put it in there. Okay. And then I'm going to take what's in F1 and put it into F0. Then I'm going to take what's in F2 and I'm going to move it into F1. Oh, you know, I didn't need this temp at all. Okay, I did something quite a little bit wrong. I didn't need the temp. Let me go back. Add F0 plus F1. Sorry about that. I didn't need this temp container after all. I knew I wasn't doing something quite right. Okay, so now I'm going to take what's in F0 and F1. I'm going to add them together, 1 plus 1, and I'm going to get 2. Okay. So at the end of this iteration, right, at the end of this one time through, I'm going to have the value 2 in here. At the end of a second time through the loop, what will happen? Well, F1 will get copied into here. F2 will get copied into here. The new F2 value will be 3. Okay. Now if I go through it again, 2 will get copied into here. 3 will get copied into here. 2 plus 3 is 5. Let's show what happens if we go through that loop one more time. 3 will get copied into here. 5 will get copied into here. And this will become 8. Okay, so let me show you number of times through the loop what happens. So at the end of 1 time through the loop, 2 is an F2. At the end of 2 times through the loop, 3 is an F2. At the end of 3 times through the loop, 5 is an F2. At the end of 4 times through the loop, 8 is an F2. Okay. So 1 time through the loop gives me 2 in F2. How do I go through the loop 1 time? Well, if index is 2, I don't go through the loop at all. Right? If index is 2, I go through the loop 0 times. If index is 3, I go through the loop 1 time. So if index is 3, I go through the loop 1 time. So let's show what that means. Index. So if index is 3, I go through the loop 1 time, and I get an F2 value of 2. If index is 4, I go through the loop twice. If index is 5, I go through the loop 3 times. If index is 6, I go through the loop 4 times. I always go through the loop 2 fewer times than the index value. Well, let's take a look back here. Wait a second. These values. Well, if index was 6, I would go through the loop 4 times, and my F2 value would be 8. 6 is 8. If index is 5, I go through the loop 3 times, my F2 value is 5. I go through the loop 3. My index is 3. I go through the loop 1 time. My F2 value is 2. My index is 3. My F2 value is 2. So here, if we just, after we finish the loop, return F2. Okay. So if an index is less than 2, so index 0 or 1, we get index, right? We get the index returned value, all right? Which is what we would expect, which is what we want. Index is 0, we get 0. Index is 1, we get 1. Index greater than or equal to 3. Then we go through these looping values and we find out what the value is. And we showed that for these values, here, it's correct. So then the question is, what about index of 2? What happens then? What's our value if index is 2? Right. The value returned if index is 2 means we don't enter this loop at all. And so we get this, 1. Is that what we expect? Is that what we want? Index of 2 gives us 1. Yep. That's what we expect. That's what we want. Okay. I want you to notice a couple of things. So this, I'm going to leave this out there for you to for you guys to run, and you can play with and see how it works. Okay. I want you to notice something. This solution here, it looks more complicated, right? It looks complex. It might be harder to understand for another programmer to look at this and understand what's going on. This looks more simple. We understand this much more easily. We have a base case, we have a recursive call, the function is defined in terms of sub values of itself. That's fine, okay. All right, so this looks more complex, this looks easier to understand. All right, but in terms of efficiency, especially if we look for really high index values, like the 100th Fibonacci number, for example, this is going to take a much longer time to calculate it than this will. Okay, and this is what we call a trade-off. If your solution needs to be efficient time-wise, there's large values we're dealing with, large arrays, large whatever, right? And you need to have an efficient way to do stuff, right? Then an iterative solution, a more complicated solution, might be best. Okay. But if, for the most part, you're not going to, you're only going to look at the first 10 values of the Fibonacci sequence, for example. Right? You may not look at really large values. Then a recursive solution, even though not as efficient, might be okay because it's going to be milliseconds difference. And so it may not be that big of a deal to have an easier solution code-wise that might not be as efficient when it actually runs. Okay, and this is basically what software engineering, as you'll find out later in your later classes, is all about, is trying to analyze, do I need a simple solution that will be inefficient, but really the less efficient solution won't be that big of a difference, right? Or do I need an efficient solution that might be a little bit more complicated, that might be a little bit harder to maintain later? Okay. All right. So we will end there for today. One thing, we will finish up our recursion stuff next week. Okay, we'll talk about some other forms of recursive things and a very special problem that we'll talk about in depth called the Towers of Hanoi. Okay, it's a very, very fun problem. You've probably played the game, a game similar to it as a child, and so we'll look at that next week. Okay, are there any other questions before we close for the day? Any questions? No. Okay. Going to be a quiz today? No, there's not going to be a quiz today. Okay. All right. So I'll see you guys next Thursday for the final class period before the final exams. And like I said, make sure to get an early start on that assignment. And if you have any questions about it, contact me and or the grader, and we'll try to answer your questions. All right. Thank you guys. Have a good weekend. We'll see you next week.